Chapter 7 Warbirds. African Americans carefully read every newspaper article about the Tuskegee Airmen, a group of black military pilots who fought during World War II. As with many other flyers, their lives depended on knowing their plane's strengths and weaknesses, and every response it would make as it waltzed through the sky. By the summer of 1944, the men of the 332nd Fighter Group were flying North American P-15 Mustangs. "It's best described as a pilot's airplane," said an American military official in a front-page article in the Washington Post. "It's very fast and handles beautifully at high speeds." With a big four-blade propeller and a Rolls-Royce Merlin engine, the Mustang sped across the sky like a 400 miles per hour racehorse. The Tuskegee Airmen and lots of other pilots considered it would be the best plane in the world. "I will get you up in the air, let you do your job, and bring you back safely," promised the Mustang to its pilots, like a trusted horse to its rider. And helping the plane to make good on that promise was now part of Dorothy Vaughn's full-time job. The Tuskegee Airmen in 1942 to 1943, location unknown. The secret weapon. But Dorothy couldn't really talk to her friends and family about her work. During World War II, the National Advisory Committee for Aeronautics wanted to defeat Germany by air, both by creating planes capable of destroying their targets and by coming up with technological advancements that would give the United States a military advantage. The Langley Laboratory was one of the United States' most powerful weapons, a secret weapon hidden in plain sight in a small southern Virginia town. While the performance of the Mustang airplanes fighting overseas was a topic of front-page news, the daily work of the West computers and the others in the lab was considered sensitive and secret. Bosses told their employees to stay on the lookout for spies disguised as soldiers, or people who might try to get valuable information from laboratory employees. AirScoop, the newspaper of the NACA, sounded the alarm. "You tell it to someone who repeats it to someone, so someone you know may die." The Langley employees took the warning to heart. Even if they had wanted to talk about their work, they would have found it difficult to find someone outside the lab who would understand what they were talking about. Off campus, people around town often found the Langley employees a bit peculiar. They had strange accents from other parts of the country. Many of them wore rumpled shirts with no ties, and some wore sandals or sported beards. Locals called them brain busters or NACA nuts. The less polite called them weirdos. What makes things fly? The pace of discovery and invention was so fast at Langley that an entry-level position there was considered by many people to be like studying at the world's best engineering school. In addition to receiving on-the-job training, employees had the chance to take classes in math and physics and other subjects that would help them further understand how to design better planes. And that's what Dorothy did. With the goal of turning women math teachers into crack junior engineers, the laboratory sponsored a crash course in engineering physics for the newly arrived computers. 2 days a week after work, Dorothy Vaughan and the other new mathematicians filed into a makeshift classroom at the laboratory for an intensive class in the fundamental theory of aerodynamics, which is the study of objects moving through the air. They also attended a weekly 2-hour laboratory session for hands-on training in one of the wind tunnels, and they had an average of 4 hours of homework on top of their 6-day work week. What makes things fly? Dorothy asked herself all day long at her job. She had never flown a plane and had never before given much thought to the question. The first course she took at Langley taught her the basics of aerodynamics. She learned that when a wing moves through the air gets cut in 2 parts. There is a slower moving airflow on the bottom of the wing and faster moving airflow on the top. This creates 2 different pressures, and it's this difference in pressure that creates lift, the most magical force that causes the wing and the plane attached to it to rise into the sky. It's important to keep air smoothly flowing around the plane. Turbulence or sudden gusts of wind can make a plane hard to control. One of the NACA's greatest achievements was designing wings that allowed planes to move easily through the air. Today, we take many of these design elements for granted, but each change came about after a series of experiments and mathematical computations. and to luck. The first inventors made some assumptions, built a plane, tried to fly it, and if they didn't die in the process, they applied what they learned to the next attempt. By the time Dorothy was on the job, the task of modifying airplane design had been turned over to the aeronautical engineers and the test pilots who flew the planes directly into their weak spots. Each time the pilots pushed the aircraft to the limit, they helped generate data that could be used to identify ways to make a good plane even better. The test pilots also risked their lives and the loss of a very expensive piece of equipment. To make the job easier, researchers developed wind tunnels that allowed them to test model planes without the danger of flying a real plane. At its simplest, a wind tunnel was a big box attached to a powerful fan. The basic idea behind the wind tunnel was that air moving at a certain speed over a stationary object was similar to moving the object through the air at the same speed. Engineers blasted air over full-sized aircraft scale models or individual parts, such as wings or bodies. By closely observing how the air flowed around the object, the engineers could assess how the object would fly through the air. Langley built different wind tunnels to test specific features of the plane. There was even a tunnel called the full-scale tunnel, which opened wide enough to swallow a full-size plane. Running the electricity-hungry wind tunnels wasn't always easy for the laboratory, because the local power company rationed electricity during the war, including for the laboratory. The NACA solved the problem by running some of their tests into the wee hours, and people living near Langley complained about the roar of the tunnels while they were trying to sleep. Despite the challenges, building wind tunnels that were quite similar to real-world conditions was one of the keys to the NACA's success. Making a good plane better. No organization came close to Langley in the quality and range of wind tunnel research data. It wasn't good enough to say a plane flew well or badly. Engineers tried to measure how the plane performed, so they developed a 9-page checklist. These experiments generated data, numbers, lots and lots of numbers. And the raw data from the tests then went to the desks of Dorothy Vaughan and the other female computers for analysis. An airplane wasn't one machine for a single purpose. It was a complex machine that could be tweaked to perform different kinds of tasks. The airplane's names or designations reflected their use. Fighters, also called pursuit planes, were assigned to the letter F or the letter P. The letter C identified cargo planes, which were built to transport military goods and troops. B was for bombers, and X marks the spot of experimental planes still in development. Planes lost their X designation once they went into production. For example, the B-29 was the final version of the X-B-29. Engineers worked hard to make each version of an aircraft better and more stable than the previous one. Discoveries large and small contributed to the speed, maneuverability, and safety of the machines. As World War II approached its peak in 1945, almost every American military airplane being produced in factories had features that were based on the research results and recommendations of the NACA. The B-29 Superfortress was a 4-engine propeller-driven heavy bomber used during World War II. It was the most expensive aircraft designed during the war. Whether data came from the wind tunnels, test flights, or theoretical models, it eventually reached the women computers so they could use their sharp pencils and sharp minds to figure out what the numbers meant. Instead of looking at just a few numbers, they looked at extremely large sets of numbers, which could be used to find patterns or trends in the ways the airplanes performed. What Dorothy and the other women at the laboratory worked on was usually a small portion of the larger task. The work was carved up into smaller pieces for quick, efficient, and accurate processing. By the time the work arrived on the computer's desk, it might be just a set of equations and numbers. Sometimes they didn't even know what kind of plane had been tested, or what the engineers were hoping to understand from their research. Once a woman finished a particular job, the calculations were taken to the engineers who used them to improve airplane designs. The computer's work was essential, but largely uncelebrated. "Woe unto thee if they shall make thee a computer," joked a column in AirScoop. "For the project engineer will take credit for whatsoever thou doth that is clever and full of glory. But if he slippeth up and maketh a wrong calculation, he shall lay the mistake at thy door when he is called to account, and he shall say, What can you expect from girl computers anyway? But sometimes a breakthrough was so important that everyone got credit. When the Boeing B-29 Superfortress was finished, it became a symbol of United States technological progress and its ability to bring destruction to its enemies. There is no one in the laboratory who should feel that he or she did not have a part in the bombing of Japan, the NACA director said to the lab employees. The engineers who assisted, the mechanics and the model makers who did their share, the computers who worked on the data, the secretaries who typed and retyped the results, and the janitors and maids who kept the tunnel clean and suitable for work, all made their contribution to the final bombing of Japan. Dorothy knew that her work was making a difference in the outcome of the war. She read the news accounts of how the B-29s, capable of flying farther, faster, and with heavier bomb load than any plane in history, dropped precision bombs over Japan from high in the sky. Dorothy found her work more intense and interesting than she had imagined, and she knew she wanted to stay for the duration of the war, and maybe longer. There was no doubt about it. Dorothy Vaughan had become one of the NACA nuts.